It started as a routine scan of deep space. Then, detailed observations and analyses changed everything, as no intercepted transmission has been reported or confirmed by any authentic sources. In July 2025, astronomers tracked 3I/ATLAS, an interstellar object flying through our solar system against all odds. Its orbital path, so rare it's been called a cosmic lottery ticket, drew the world's attention. But when Space Force monitoring was noted in public discussions, scientists were left reeling, though no signal has been detected or declassified. Could this be the first clue of something engineered? Or is nature playing with our expectations yet again? If 3I/ATLAS truly exhibited anomalous behavior beyond natural explanations, the consequences could rewrite our understanding of who or what is out there. Before we jump to conclusions, let's dig into the facts that sparked this unprecedented cosmic puzzle, incorporating the latest confirmed data from NASA, the Minor Planet Center, and telescope observations. 3I/ATLAS carries a name that signals its extraordinary origin. The 3I means it is only the third confirmed object to enter our solar system from interstellar space. The official designation C/2025 N1 Atlas tells its own story. C stands for comet. 2025 N1 marks it as the first such discovery in the second half of July 2025. And Atlas points to the survey that found it, the Asteroid Terrestrial Impact Last Alert System. That survey operates out of Rio Hurtado, Chile, and has a track record for spotting cosmic wanderers before they become headlines. The discovery took place on July 1st, 2025, when the Atlas telescope caught a faint moving point of light at a distance of 4.5 astronomical units from the Sun, about 670 million kilometers out, near the orbit of Jupiter. Within days, astronomers confirmed this was no ordinary visitor. Its path through space does not loop back toward the Sun like a native comet. Instead, it follows a hyperbolic trajectory, meaning it is just passing through, never to return. That is the signature of an object born far beyond our solar system. The International Astronomical Union's Minor Planet Center reviewed the data and assigned the 3I prefix following the rules set after the discoveries of 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Each of these rare objects gets a number in the order they are found along with the I for interstellar. Atlas became the third in this exclusive club and the first to show clear signs of cometary activity right from the start, with observations confirming outgassing and a developing tail as it approached the inner solar system. Early images revealed a fuzzy coma, a cloud of gas and dust surrounding a solid, icy nucleus. Hubble Space Telescope measurements suggest the core could be anywhere from 0.3 to 5.6 kilometers wide, with a likely size under 1 kilometer. The coma itself stretches up to 15 miles across, formed as the sun's heat causes the ices to sublimate and release dust. This behavior matches what is expected from a comet, but with a twist. The object's high and open-ended path confirm its alien origin. Finding 3I/ATLAS was not just a matter of luck. The Atlas team, along with other surveys like the Zwicky Transient Facility, pieced together pre-discovery images that traced its journey back to mid-June. Amateur astronomers also contributed, noting that the comet had slipped through crowded starfields near the galactic center, making it nearly invisible until it emerged into clearer skies. Only coordinated global effort and advanced detection algorithms made this catch possible. The official press release from NASA and JPL made it clear. 3I/ATLAS is a true interstellar visitor, not a fragment from our own solar system. Its velocity, 58 kilometers per second relative to the Sun, places it far outside the gravitational grip of our star. This is a one-way trip, and the comet's approach is a rare astronomical event. The international community quickly mobilized, setting up observing campaigns to capture every detail before the object fades back into the darkness between the stars, including multi-wavelength studies by JWST and SPHEREX that revealed its high carbon dioxide content and unusual gas ratios compared to typical solar system comets. For astronomers, the arrival of 3I/ATLAS is both a triumph of technology and a reminder of how much remains unknown. Each new interstellar object brings a chance to test theories, refine models, and maybe, just maybe, uncover something that changes our understanding of how the universe works. The story of 3I/ATLAS begins with a name, a discovery, and a set of physical facts that place it firmly among the most intriguing objects ever tracked by human eyes. 3I/ATLAS doesn't just pass through the solar system. It threads a path that has left even seasoned astronomers shaking their heads. Its orbital inclination sits at 175 degrees, which means it's moving almost perfectly retrograde, skimming just 5 degrees off the ecliptic plane. Statistically, the odds of an interstellar object arriving with this kind of alignment are about 0.2%. 2 in 1,000. That alone would be enough to raise eyebrows. But the story gets even stranger when you look at its planetary encounters. As it barrels inward, 3I/ATLAS will pass unusually close to not one, but 3 major planets: Venus, Mars, and Jupiter. According to the calculations from Hibbard, Crary, and Loeb, the probability of an interstellar object randomly achieving this triple alignment is just 0.005%. In practical terms, that's about 1 in 20,000. For most comets, a close brush with even a single planet is rare. 3-in-1 journey defies any reasonable expectation of chance. What makes this trajectory so unsettling is its precision. The object's approach to Mars in early October 2025 comes within 30 million kilometers, a cosmic hair's breadth, while its path past Venus and Jupiter is similarly tight. And all of this happens while 3I/ATLAS maintains a velocity of 58 kilometers per second, the fastest of any interstellar visitor we've tracked. These aren't just close calls. Each encounter is timed with a level of synchronicity that stands out against the backdrop of random cosmic motion. The retrograde orbit adds another layer. Most objects from beyond the solar system approach at odd angles, but 3I/ATLAS is nearly coplanar with our planetary system, just moving the opposite way. This alignment isn't just a quirk of celestial mechanics. It's the kind of trajectory that, if engineered, would be ideal for observing or even interacting with multiple planets in a single pass. The object's perihelion or closest approach to the Sun occurs on the far side from Earth. That timing isn't lost on researchers. It means the Sun itself blocks our view during the most critical phase, making detailed observation nearly impossible. Harvard astronomer Avi Loeb and his colleagues have pointed out that if someone wanted to design a probe to maximize surveillance opportunities while minimizing the risk of detection or interception, this is the kind of path they'd choose. The calculated odds, 0.005% for this sequence of planetary flybys, are so low that some in the field have begun to question whether pure chance can account for it. For now, 3I/ATLAS remains a traveler whose route looks less like a random dart and more like a carefully plotted course. That's why, as the object continues its journey, astronomers and defense agencies alike are ramping up their monitoring. When the numbers break this far from expectation, the question shifts from what is it to why here and why now. Recent simulations and orbital refinements confirm the close Mars flyby on October 3, 2025, at approximately 30 million kilometers, with ESA's Mars orbiters poised to capture data, while approaches to Venus on November 3rd and Earth on December 19th are farther but still notable for study. The United States Space Force operates some of the most advanced listening posts on Earth. Their mission goes far beyond tracking satellites or cataloging space debris. The Space Surveillance Network, for example, can pinpoint objects as small as a marble in low Earth orbit. This isn't just about keeping tabs on old rocket stages, it's about catching anything that stands out, no matter how faint or fleeting. At the heart of this system is Space Fence, a radar array on Kwajalein. Space Fence can scan the sky continuously, detecting thousands of new objects each day. Its sensitivity is so high that it can spot fragments just centimeters across, even at distances of several thousand kilometers. If something unusual enters the radar's field, say a fast-moving object from beyond the solar system, Space Fence would notice. Every unidentified blip is logged, tracked, and compared against known objects. Anything that doesn't match gets flagged for further scrutiny, but Space Fence is only one layer. The Deep Space Advanced Radar Capability, or DARC, is currently rolling out in Australia, the UK, and the US. This system is designed to monitor the geosynchronous belt where most communication satellites orbit. DARC uses multiple antennas working in concert, building a detailed picture of everything from routine satellite maneuvers to unexpected newcomers. Together, these networks form a kind of digital net ready to catch even the rarest interstellar visitor and anything it might bring with it. Space Force calls this mission Space Domain Awareness. That means understanding every object, every signal, and every anomaly in the space environment. Their mandate covers not just tracking, but also rapid identification of anything that doesn't fit established patterns. If a signal or transmission were ever linked to an object like 3I/ATLAS, these are the systems with the ears to hear it. The infrastructure exists. The question is, what if anything stands out from the cosmic background? However, as of current data, no such signal has been reported or confirmed in association with 3I/ATLAS, with observations focusing on its natural cometary properties instead. Separating a genuine signal from the background noise of the universe isn't as simple as catching a blip on a screen. Astronomers rely on a strict checklist, one that's been refined by decades of both excitement and disappointment. The process starts with raw data, often gathered by radio telescopes scanning frequencies in the so-called waterhole band, a quiet patch of the spectrum between 1,420 and 1,666 megahertz. This range is favored because it's relatively free from cosmic and human-made interference. And it's where SETI scientists expect a deliberate transmission might hide. But a spike in this band isn't enough. Every candidate signal faces a battery of tests. First, researchers check for Doppler drift. Think of the way a passing ambulance changes pitch. If the frequency of a signal shifts in a way that matches the motion of an object in space, it's more likely to be real. The famous WEOW signal from 1977 passed this test, showing a drift that matched expectations for a cosmic source. Still, it was never repeated. And that's another hurdle, repeatability. A true signal should reappear when the telescope points at the same spot, or at least show up in another observatory's data. One-off events are always suspect. Next comes the on-off test. Astronomers alternate between the target and nearby blank sky. If a signal vanishes when the telescope moves away, then that's a good sign. If it stays, it's probably local interference. Maybe a passing aircraft, a satellite, or a piece of electronics on distant Earth. SETI teams also cross-check with databases of known transmitters, satellites, and even microwave ovens. The goal is to rule out every mundane source before even whispering the word anomaly. Modern searches add a final layer, machine learning. Algorithms can sift through millions of candidates, flagging only those that survive every filter. Even then, the process is slow and methodical. SETI veterans like Sophia Sheikh and Dan Wertheimer have described it as looking for a whisper in a hurricane. Most signals, even the promising ones, turn out to be false alarms. That's why when something survives the checklist, astronomers pay attention, but always with a dose of skepticism. False positives are the rule, not the exception. In the search for signals from deep space, every promising candidate is put through a battery of tests designed to rule out the mundane before anyone entertains the extraordinary. The BLC-1 incident in 2020 is a textbook example. During a breakthrough listen at the Parkes telescope in Australia, researchers picked up a narrow-band radio signal at 982.002 MHz while scanning Proxima Centauri. On paper, it looked like the real thing, a persistent drifting tone that showed up only when the telescope was pointed at the star. The signal lasted over 5 hours across multiple sessions with a drift that mimicked what you would expect from a transmitter on a rotating planet. For months, the team tried to break the case. They ran the data through every filter, Doppler drift, on-off pointing, cross-checks with other telescopes. Nothing obvious gave it away. It passed the initial checklist, a rarity in SETI work, where most signals are quickly exposed as interference from satellites, aircraft, or even microwave ovens. But the investigation did not stop there. The team led by Sophia Sheikh dug deeper. They found over 100 look-alike signals scattered in the dataset, each with the same drift signature as BLC-1, but showing up in off-target scans. That was the smoking gun. Further analysis traced the source to a complex blend of human-made radio interference, specifically intermodulation products from electronic devices near the telescope. The frequency, the drift, even the persistence, all matched what you would expect from overlapping signals bleeding into the telescope's sensitive receivers. B was not a message from Proxima Centauri. It was a whisper from Earth's own technology, dressed up by chance and complexity. This is why astronomers approach every new signal with a heavy dose of skepticism. The high false positive rate in SETI is not a bug. It is a feature. Each candidate is assumed guilty until proven innocent by a process that is part detective work, part engineering audit. Only after every possible source of interference is eliminated does a signal earn the right to be called an anomaly. Even then, as BLC-1 proved, the odds still favor a false alarm. That is the reality behind the headlines. For every signal that survives the gauntlet, hundreds more are quietly demoted to the archives of radiostatic. This rigorous approach ensures that any claims about signals from objects like 3I/ATLAS remain grounded, with current data showing no such detections despite extensive monitoring. Avi Loeb, a Harvard astronomer known for his willingness to challenge scientific orthodoxy, has proposed a new way to classify interstellar objects, the Loeb scale. This system, published in August 2025, gives each object a rating from 0 to 10 based on how far its behavior strays from what physics predicts for natural comets or asteroids. Level 4 is where things get uncomfortable for conventional explanations. That's the rating assigned to both 1I/ and now 3I/ATLAS. A level 4 tag means the object displays multiple persistent anomalies that resist easy explanation. For 3I/ATLAS, these aren't minor quirks. Its trajectory brings it unusually close to 3 major planets, Venus, Mars, and Jupiter, with a statistical chance of about 1 in 20,000 for such a sequence to happen by accident. The orbit is nearly coplanar with the solar system, but retrograde skimming just 5 degrees off the ecliptic. Add in its size potentially up to 5.6 kilometers across, and you have a combination that stands out even among rare interstellar visitors. Loeb and his colleagues have argued that if someone wanted to design a probe to maximize planetary flybys while minimizing the odds of interception, this path would be ideal. The timing of perihelion, when the object passes behind the Sun, as seen from Earth, means the most critical phase is hidden from our best telescopes. It's the kind of stealth window that would interest anyone with something to hide. Some researchers point to the dark forest theory, a scenario where intelligent civilizations avoid detection for survival, as a possible motive for such engineered caution. Loeb's team even ran simulations showing that a reverse Oberth maneuver at perihelion, using the sun's gravity to slow down, could allow a probe to drop into orbit around the sun or deploy smaller devices toward nearby planets. While most astronomers remain skeptical, the Level 4 rating signals that 3I/ATLAS sits at the intellectual edge of what's possible. It's not proof of technology, but it is an open invitation for continued careful observation. As the object draws closer, every new data point could tip the balance between natural oddity and something engineered. For now, the only responsible stance is to keep watching, keep measuring, and let the evidence lead wherever it will. Debates continue, with Loeb's suggestions countered by observations from HST and others showing typical cometary features, though his papers highlight the object's high speed and alignment as worthy of further scrutiny. New eyes are joining the hunt for interstellar mysteries. The Vera C. Rubin Observatory, set to begin full operations in 2026, will scan the southern sky every few nights with an 8.4-meter mirror and a 3.2 gigapixel camera, the largest digital camera ever built for astronomy. Rubin's survey is expected to spot dozens of interstellar objects every year, compared to the handful found so far. That means the odds of catching something even stranger than 3I/ATLAS are about to jump dramatically. More data points, more orbits, and more chances to spot patterns or outliers that challenge what we think we know. On the radio side, the Square Kilometer Array is preparing to open a new chapter in signal detection. When completed, SKA will be the world's largest radio telescope, stretching across South Africa and Australia. Its sensitivity will let astronomers pick up faint signals from deep space, mapping hydrogen across cosmic time and searching for narrowband transmissions that could hint at technology. SKA's design allows for rapid follow-up on any anomalies flagged by other observatories, making it a powerful tool for cross-checking anything unusual that pops up in Rubin's data or in the radar nets of Space Force. The scientific community is gearing up for a future where interstellar objects become a routine part of the nightly sky survey. With next-generation instruments coming online, the process of checking, tracking, and decoding these cosmic visitors will only get faster and more precise. Each new detection brings the possibility of another puzzle, another anomaly, or maybe even the answer to a question we haven't thought to ask yet. The story of 3I/ATLAS is just one chapter in a much bigger book that's still being written.